Hey, everybody. Happy Thursday. It's another beautiful day in Boone. All kinds of different modes of water coming from the sky. I would like for you to please tell me what is your pet peeve today in the chat for attendance. What is your pet peeve? And while we're doing that, let's talk about homework 2. What do you think about homework 2 in general, people? Give me some feedback.
Once I figured out how to do it, it wasn't too bad. I definitely had to use like internet resources to figure out some of the coding stuff. But like I said, once I figured it out, it wasn't bad.
Okay.
Only issue I had was with the line of best fit, and I did eventually just figure that out. I just had to put it in manually.
Okay, what else? What else about homework 2?
It definitely took a little while to figure it out because I just kept getting errors for everything. Even when I followed your example, it didn't work the exact same way for my computer and I guess my code.
Okay,
So
and so was that
figure it
with
out.
graphing? Was that with plotting, Veronica, or with other things?
That was actually with trying to input Excel and trying to do it the way that you did it in homework 0.5. I tried doing that. It took a little while to figure it out, but I eventually got it.
Okay. What else? Homework 2. Okay. So when I assigned homework 2, I was not clear, but I did not mean for you to do the whole thing in Jupyter Notebook. I meant for you to use Python to make the plots. So the way that I wrote it, it didn't, I'm sorry, it was not clear. If something like that, happens in the future where it's taking you a really long time, in the case of just trying to show a table, or set some sort of special symbols or something. If that's taking you a long time in Jupyter Notebook, I don't want you to spend a lot of time on that. I don't want you to waste time ever. So I really just want you to use Jupyter Notebook and Python this semester for making plots. And you don't really have to use it for typing out words and typing out problems. You can if you want to, but I really just want you to use Python for making plots. So I'm sorry that wasn't clear with homework 2. And if you ever feel like a homework is taking way too long and it's like bullshit, I really want to know. I really hate bullshit. And I don't want you to waste time. So tell me if that's happening, and then we'll figure out a solution. So thank you for those of you who did communicate about homework 2. The earlier the better, though. Then we can identify problems right away. Any other stuff about homework or comments about class, questions? Any questions at all? All right, what we're going to do is we're going to throw you immediately into breakout rooms today. I want you to go to the website and go to this link, in class problems 2.9 and 2.11. It's the same ones we were looking at last time. So I want you to do the Snell's law problem, okay, in your breakout rooms, please. All right, we already did the other ones at the top, A, B, C, D, E. Now we're going to do this Snell's law question. So I'll leave it up here, but also go to the As You Learn page. Again, it's under this link in class problems 2.9 and 2.11 to get to this problem. All right, I'm just going to scroll over here for a moment to copy this. All right, your breakout room assignments are in the chat. Now I'm going to go open up those breakout rooms. All right, you should be able to go to your breakout rooms now. Okay, I think we're back pretty much. Welcome back, everybody. Did y'all get a result? Does anybody, any of the groups get to a final answer?
We got to one.
Okay,
I got to one.
cool. Abdel, can you give us your answer? I think
Yeah,
that
we
was you
got-
talking earlier.
Yeah, we got 3%, like one sig fig and everything.
Okay, 3%. What about, yeah, okay. For N2. All right. Anybody else get anything different? Or did you also reach the same result? Okay. All right, so thank you. Let's go through that quickly. You can see the result. The solution is on the As You Learn page, posted there. Let's go through it real quick. We know Snell's law, N1 sine 1 theta, sine theta 1 is equal to N2 sine theta 2. We're given that theta 1 is 22.0 degrees plus or minus 2 degrees. Theta 2 is 14.5 plus or minus 0.2 degrees. When we convert those to radians, we get these values here that I'm circling, and we keep the same number of sig figs for the measured quantity and the uncertainty. We're also told N1 is 1.0000 and has doesn't really have an uncertainty that we need to propagate. Okay, so when we isolate N2, we calculate 1.50. Notice that I could have used the small angle approximation for the denominator. It wouldn't have really made a big deal. If I had used the small angle approximation, then sine of theta, sine of 0.253 is equal to 0.253. And I would have put just 0.253 here. And if I use the small angle approximation here, though, sine of 0.384 is kind of, 0.384 is pretty off somewhat from 0.375. So anyway, I didn't use the small angle approximation here. And I got 1.50 still with the 3 sig figs we started with in our measured quantities. To calculate N2, we find the fractional uncertainty, which is the sum of the uncertainties of the individual functions making up N2, functions of theta. So N1 is a constant, and it's going to cancel in my fractional uncertainty. So sine theta 1 is my first function. So I have delta sine theta 1 over sine theta 1, and sine theta 2 is my second function. So I have delta sine theta 2 over sine theta 2. I square those, add them, and that's going to allow me to get to my final value of delta N2. Okay, for the denominator, we already know what theta 1 and theta 2 are. The uncertainty, or the delta sine theta 1 and delta sine theta 2, need to be converted into a simple function. So cosine of theta 1, delta theta 1. So now we have quantities we can substitute here. We didn't really have something we could substitute for delta sine theta 1. And same thing for delta sine theta 2. We need our that delta sine theta 2 to be in terms of something we can substitute. So we convert to cosine theta 2 delta theta 2. We know what delta theta 2 is. It's the uncertainty in theta 2. All right, so we substitute our quantities and we get, as Abdel was saying, 0.03. And then since delta 2 is 0.03, we can calculate delta N2. It's going to be N2 times 0.018. Sorry, that's how we got to the 0.03 over here. When we multiply N2 times 0.018, we get 0.028. And we round that to 1 sig fig, 0.03. So my final report, the way I report this, is N2 is 1.50. That's what I calculated up here. Plus or minus 0.03. All right, now that's not the same thing as 3%. But maybe that's what you meant, Abdel?
Oh no, I did the wrong thing. That's why I got different, I think.
Okay.
Yeah.
All right. Did anybody have questions about that or?
I have a question, Dr. Astor.
Okay. Mhm.
So I've been using this handy rules for propagation of error sheet that you posted on As You Learn for
Mhm.
last week. And for the general formula for multivariable functions, it doesn't do anything with fractional uncertainties. It just has the uncertainty of Q is equal to the derivative times the uncertainty rather than the derivative times the fractional uncertainty.
Okay. Let's see if I can get that up here. Yeah, I didn't actually get to the general formula yet in class, as you probably have noticed. We were going to do that today. I don't have my As You Learn page up here. Yeah, I can show you the general equation really quick. Hopefully this is what you're using. I think that's Henry talking. Is this what you're using, Henry?
Yeah, that's what I was using. But isn't that different than what you used?
Well, in my case, Q is sine theta and X is theta. So I took the derivative of sine theta with respect to X. I got cosine theta and then multiplied by the uncertainty in theta. So how did I mean, maybe you can explain to me what you did.
Yeah, I mean, that is what I did.
How what you did is different.
Well, I thought that if we look back at the answer, I thought that that you had done fractional uncertainties instead of just regular uncertainties.
Okay. Well, they are derivatives, actually, because this is a derivative of Q with respect to X. Sorry, I'm trying to get back to that.
In the working out, the
There we go.
professor divided by sine theta, which is why it's fractional uncertainty.
Yeah, I know that.
So yeah, that also you have to do it twice because it's division as well.
Okay, so this is what you're talking about, Henry?
Yeah,
Because I divided by sine theta?
right. Yeah.
Okay. Yeah, so I was trying to follow what we were doing in class last time with just our trigonometric functions and not really use that general formula yet. So let me like revisit this and make sure it should be consistent either way. And I will make sure. Other questions about this example, Snell's law? Or did anybody have other ways that they did it? in their groups. Okay.
What did the final uncertainty come out to be again?
I got 1.50 plus or minus 0.03. So I will check, I'll double check and make sure that works with the general propagation. Should be the same. All right, we're going to continue on with finishing up presenting this general equation for propagation of uncertainty. So let's review partial derivatives real quick, because maybe we don't remember. Partial derivatives, or maybe we've never seen them before. We, in this case, are looking at an example. We have a partial derivative of q with respect to z. Okay, so if we're going to take this partial derivative, what we do is we substitute q up here, which is x squared, y squared, z squared, and we treat everything except z as a constant, or a function of z as a constant. So if I had like e to the z or sine of z or something like that in my q, then I don't treat that as a constant. But x squared has nothing to do with z, and y squared has nothing to do with z, unless I'm told otherwise. So I'm going to treat x squared like a constant and y squared like a constant in this partial derivative. Okay, so that means I'm going to take x squared and y squared and write them in the derivative, and then I'm going to take the derivative of z squared and put that in to z. So there's my partial derivative example. We are going to be using partial derivatives in our general function for error propagation, which should still match up, like we were saying, with previous rules that you've already learned for error propagation. So here's our general function. If we have q is a function of x, y, and z. X, y, and z are measured quantities. Q is a calculated quantity or mathematically determined quantity with the measured values. Then the uncertainty in Q is going to be equal to the uncertainty in Q partial derivative of Q with respect to the first variable, x, times the uncertainty in x, that quantity squared. And then we're going to take the partial derivative of q with respect to y, the next variable, and multiply by the uncertainty in y and square that quantity. And then we will take the partial derivative of q with respect to z, multiply by delta z and square that quantity and add them up and take the square root to find delta q. Something that may have been confusing earlier, Henry, is I had delta q over here on the left-hand side. So that probably was confusing. I didn't have just delta q. Okay, so this is our general function. We should be able to use this for any function. It's kind of overkill if we don't have something complicated, but we should be able to use this for any function, even multivariable functions. Right. Back to breakout rooms. Let's do this example. We have q is equal to x times e to the minus y. Wait a minute. Wait a minute. Hold on one second. I'm going to repaste this. I already did this. Hopefully you didn't see the answer there. I kind of showed you for a moment. All right, we have q of x, comma y. And it's equal to x times e to the minus alpha y. Alpha has units of 1, or alpha is equal to 1 inverse centimeters. X is equal to 20 plus or minus 2 watts per centimeter squared. So that's a measured quantity. And y is equal to 1.0 plus or minus 0.1 centimeters squared. That is the measured quantity. Alpha is a given constant. It doesn't have any uncertainty. It doesn't contribute to your sig figs or anything. So what you're going to do is find Q and find the uncertainty delta Q using that general propagation formula. So go back to your breakout rooms when you're ready. They should still be there. And we'll take 5 minutes and meet back here at 4:36 or so ish.
I no longer see my breakout room.
Oh, you don't see
They're
them? Okay,
cl-
I'll
yeah, they're closed.
redo the breakout rooms. You can still see your assignments, I think, right?
Yeah.
Okay. Oh, here we go. Should work now. There's the problem. Sorry, Ethan. There you go. Okay, anybody got an answer yet? Q is equal to what plus or minus what?
Well, we got a answer.
Yeah, I got an answer too.
Okay, what'd you get?
You want to go first, Abdel?
Yeah, sure. I got 7 plus or minus 1.
I got 7 plus or minus 1 also.
Oh,
Me
good,
too.
good.
Me too.
Okay.
Anybody else get 7 plus or minus 1?
I got
Great.
I did.
saw a nod. Great. Okay. So let's look at my answer real quick, and then we can talk about mean standard deviation real quick before we have to go. All right, here's the question at the top. Q is in blue because it's a mathematically determined value. X and Y are in green because they're measured values. And we're using that general form of error propagation equation here. So X and Y are our 2 variables, so we don't need the Z term from our original equation. So first I found delta Q over delta X, or partial derivative of Q with respect to X. So that means we're going to take this function up here, and X is the variable. So e to the minus alpha Y is the constant, and it stays behind, and the X goes away. When we take that derivative, we substitute alpha, we substitute Y, we get e to the minus 1.0, and their units cancel, and that's 0.3679. Then the partial derivative of Q with respect to Y is going to be the derivative of this thing with respect to Y. So X is a constant and it comes along for the ride. And then we take the derivative of e to the minus alpha Y with respect to Y. So that minus alpha comes down to the front and we get this as our derivative. and we substitute all those values in and get minus 7.3576 with lots of sig figs because I'm just carrying them all through right now. Watts per centimeters cubed for that one. Notice there are units happening here, and I'm carrying the units through so you can see how the units of Q should end up being the units of delta Q. And if the units aren't working out, something's wrong with your math. All right, so delta Q, I'm going to substitute stuff into this equation up here. I have this partial derivative, 0.3679. I have this partial derivative, minus 7.3576 watts per centimeter cubed. I substitute my uncertainty in X here. I substitute my uncertainty in Y here. I square stuff, I add it, I take the square root, I get 1.041 watts per centimeter squared. So that should be watts per centimeter squared, and it is. Should match the same units as the quantity. I calculate the quantity itself. It's 7.3576 watts per centimeter squared. I know I'm only supposed to have one sig fig and my uncertainty, so I round this to 1. Could have rounded it to 2, but that seemed really close to 1. So I didn't round that up to 2. So I have my 1 sig fig here, which means I have 1 sig fig in my Q, 7 plus or minus 1 watts per centimeter squared. Good job, people who got that. Questions? Comments? Great. Moving on to mean and standard deviations. That's like the whole theme of this week, and we have 6 minutes left. Awesome. For the week. So there'll be some adjustments in the As You Learn page coming up, since I'm having so much fun doing problems. I don't know about y'all, but I just like to do math. Okay, so random effects and systematic effects. Let's talk about those real quick. We've talked about them a little bit, but we're going to revisit this. Random errors are unpredictable, and they're just as likely to land above or below the true value. That's what makes them random. If the true value of this quantity is red and it's being measured over time, there's some randomness happening, and there's just as much randomness at the top as there is at the bottom, over the red line as below the red line. This is a situation where we can show the average value. Let's say the average value of the fluctuations here is blue, and the accepted value is red. And they're really close together. I couldn't get these closer together without them literally like being on top of each other in the figure. So just pretend they're like literally on top of each other, but you can't, but you can still see them. In this case, the average value of our measured quantity that has this random thing going on is equal to the accepted value. If this wasn't random error, then there would be more happening above or below. It wouldn't be random anymore. Random means there's the same amount on above and below. So that's a way to think about random error. We can minimize random error by taking an average, right? Like I got rid of that above and below effect, that randomness, by taking an average of the values across this data set here. But that's not going to completely eliminate my random error. Obviously, I need to record several values. I need to repeat my experiment several times. How many times? How do I know how many times to repeat my experiment to get rid of these random errors in a good enough way? So that's a question we're asking. Let's think about systematic effects now instead of random effects. Here's some different examples of graphs showing systematic effects here. The ones up here have larger systematic error. The ones down here have smaller systematic error. They're all showing systematic error. The average measured value is blue. The accepted value is red. Those are shown here in the plots. Hopefully you can see that. A little bigger. So here we have a red accepted value up here. And here's my measurements of that value, a whole bunch of different data points, and their average is down here, this blue value. They are grouping around the wrong average. So that's a systematic error. This is pretty far away from the true value. So that's a large spread, a large error away from the average value. And then the measured average value is pretty far from the true accepted value. We have a large spread here as well. Okay. Here we have another large kind of spread around our incorrect average value again. At the bottom, the average value is wrong here, and the average value is wrong here, but the spread is less. So it's a smaller systematic error. Okay, so that's what we're looking at in this slide. We can still see some random effects, some random error here. We're not saying that it doesn't exist in this picture. We're just talking about the systematic error because it's nice and obvious for us. Okay, so let's identify which of these is large or small for both. Or neither. Is the random error large, or is the systematic error large, or is the random error big, or is the systematic error big? Another way to say random error is statistical error. Those are like synonyms with each other. So in our first example here, we have a whole bunch of data points close to each other. So a pretty small statistical spread. So that's a small statistical error. And the systematic error is large. It's the value, the average value of that systematic error is pretty far away from the true value, the red dot. Here we have a large statistical error. My randomness is spread out in a much bigger way, much further away from the true value. So I have a large statistical error. My systematic error is small though, because I'm not really, my average is still correct. It's just I'm very spread out around it. So I don't have my values all shifted off to one side. It's like a symmetric wrongness around my correct value. So that's a systematic error that is small. Okay, here I have a large random error, a large statistical error, because my points are spread out all over the place. And then my systematic error is large because they're not spread around evenly. They're spread around up here in this top half. So that makes my systematic error large. So kind of two different ways to have large systematic error. You can either have them all really far away from the correct value, or all far apart from each other and asymmetrically distributed around the correct value. And then we're going to have small random error and small systematic error if all of our points are very close and evenly distributed around the true value. Okay, so why do I care about all this? Well, I want to always make my experiment the best I can. I can usually identify systematic errors in my graphs because this asymmetry definitely stands out. So that's a little easier to identify and then fix in your experiments. Randomness is harder. Either way, if I can identify small or large systematic and random errors, I can better identify how to fix those errors and make my experiment better, make my final outcome better, my final measurement better, more accurate, more precise. Questions? I'm supposed to stop now. You're all wonderful for listening to me this long. I'll stay around if you have questions, but I think we have to stop.
Thank you. Have a wonderful weekend.
You too. Y'all have a wonderful weekend too.
Thank you.
Thank you.